first talk about standing waves on a string under tension. So let's see here. I'll bust that up here. So first thing we saw when we watched that video was these would be those two fellas handling that spring. Oh, is it not? So this is a representation of that first standing wave, some wave under tension, and what we call these things here, call those nodes, okay? Meaning fixed points where the wave is sort of like pinned down. The wave vibrates around the node, and that node isn't moving. Everything else is moving in the waveform. And we're talking about matter waves because a string is material, it's matter. Guitar strings, the spring we saw in the video, etc. And then, so if those are nodes, then this thing here is an antinode, right? Now, some things to notice here is we have a length L here, all right? And that's only half of a waveform. Technically speaking, this waveform would need to go all the way over here another distance L before we could say that we have a full wavelength. That's one complete cycle. Peak, valley, back to where it started. That's the main idea, okay, with waves. And so what we have here is this wavelength here, all right, is or L rather, is equal to half of a wavelength. Or you could call it this thing equals 2L, however you want to look at it. And so we have this interesting piece of the puzzle. Now what if I do that first harmonic bit, all right, where the wave does that sort of thing, and so that would be, as you saw, you know, it was vibrating. That's back and forth that we saw. And again, we have our nodes here, and the antinodes would be in between. But here we have this length L, and this also happens to be the wavelength. It's one complete wavelength. So up here, if you remember, they called this one, this is the fundamental mode, So you have modes and nodes, and then we have our first harmonic down here. So the fundamental mode is one big standing wave. It's the easiest, simplest one to pay attention to. All right. And we could, here's the pattern, fundamental node, the length is half lambda, or lambda is double the length, all right? And then we get lambda equal to the length. But there's the length of a string with some resonant frequency on it that's on a standing wave is always going to be some whole number of half wavelengths. That's the pattern. That's a weird way to look at it, but it's there. The length of the string can always be thought of as some whole number of half wavelengths. And all we did, well, we can take note of that in retrospect, and maybe we could have seen it first, but every time I can express the length of the string as some number of half wavelengths. It was 1 half wavelength in the fundamental mode, it was 2 half wavelengths or a full wavelength in the first harmonic, n equals 2, fundamental mode, n equals 1. Do one more just for pattern, having more than 2 elements in our pattern. So we could put another node in the middle of that length. It's a pretty crummy waveform, but all right. So we still have this length here, but now this right here, that's our wavelength, lambda. Is that funny looking letter? And you know, these nodes that we see here, so here lambda is 2/3 of the length. So we see this if we look, and then we get lambda equal to 2/3 of the length. Okay, so what are we going to do? Well, first we need to think about the most basic wave equation, and the speed of a wave, the linear speed of a wave, some point on it, all right, any point that's moving, will be equal to this lambda f. So lambda, just to be sure, so this is a linear speed. This is what we call the wavelength. And this is the frequency. All right? So frequency, if you remember, frequency is 1 over the period. It's inverse seconds, okay? Remember, that's period, which is time for one complete cycle. One whole trip around the block, if you will. And so what you have here, when you have lambda f, you literally have a distance over a time. Because that would be, if you change the f to 1 over t, you have lambda over period. All right? This is lambda times 1 over t, which would be lambda over t. So you have a distance over a time. So it's just an angular way to express the first zeroth law. Distance over time, it's just that this is a wavelength kind of distance. And it's a particular time. Time for that wavelength to be sorted out. So it's really nothing new, it's a new version of an old thing. A new version of a change in motion like we saw with just regular along a straight line changes. All right, so this equation is the basic equation that we would use in this wave game, if you will. So the pictures, and it was 2 half wavelengths out of 3 possible half wavelengths. It's the third harmonic, where n equals 3. Back here, we have lambda equals 2L, and we have this thing that V equals lambda F, then that means the frequency could be written as speed over lambda. All right? Okay. So, whoops, I'll take that back. We could write it that way. Okay. Well, I think you can, hopefully you can see that we could easily move this around, and instead of having lambda or 2L on that side, I could express frequency. And so this would be frequency of that fundamental mode, that first frequency that we drew with the one huge half wavelength, if you will. So we have that one. We also had lambda just equaled L. And so that would lead me to a frequency for that second one. That was frequency 1, that was frequency 2. So changing the frequency, remember the harmonic from just playing an open string on the guitar, and then I hit that other one and it gave it a higher, that was a higher frequency. You heard the higher frequency of that harmonic, that first harmonic. And guitars only have one at that 12th fret. Well, not exactly, but we'll pretend for now. And so that means the frequency in this case would just be V over L for that second frequency. And then in the third one, still have the same wavelength, and it equaled 2/3 of L. All right, and again, we would have V over that third frequency. And so now, when you flip all of that around, you get the third frequency is a 3V over 2L. So I want to let's focus in on these three frequencies in terms of V and L. All right? So they both have an L in the bottom, and the first frequency has nothing multiplied. First and second frequency have nothing multiplied to the V, but the third frequency does. I could write a 2V over 2L in there, and we can always put a coefficient of 1 into the game here. So what we do have this pattern where I can look at this commonality of double the length in the bottom, and then I have this pattern of a 1 times, a 2 times, and a 3 times. All right? And so what this would let me do is write a general equation. The frequency in terms of the number of modes, okay, would be some number n, an integer number, V over 2L. And really what this is telling us, and we have to go back and look at it. So I guess if we wanted to, and we do, there is a law we could write here. And we could say the length of a string with some resonant frequency producing a standing wave is always a whole number of half wavelengths. So there we go. The length of a string with some resonant frequency producing a standing wave is always a whole number of half wavelengths. So that number n has to be an integer to do that. All right, so we can predict what frequencies have that property, some harmonic property with these vibrations. So that's about as easy as it gets when you look at wave functions. I guess one other thing we could write here is that length would be some number of half wavelengths. All right. So these three equations, this is our basic wave equation. It's not the main wave equation. If you look up wave equation, you get something far more complicated, close to what we're about to do. But this is it. I mean, for waves, this is the fundamental equation, if you will, which is, if you want to think in terms of first zeroth law, it is essentially that. Speed is a distance times a time. Just frequencies that unusual. It's 1 over that total time. Okay? So we have that. And if only all of wave stuff was this simple. Unfortunately, it's not. And so we have a bit more complicated thing to do. So waves, whether they're sound waves, water waves, you name it. Light waves, electromagnetic waves, waves are waves are waves. They interfere with one another, and they can do that in constructive ways or in destructive ways. By constructive ways, meaning two waves coincide with one another and they produce a larger wave. All right? Or two waves coincide with one another and cancel each other out in some way, either completely or partially. That's the idea with these waves. So you have some stuff on sound that we're supposed to read, play, do those labs and whatnot. So we last week we did bring out of the box an equation like this one. Okay. And since we're talking about an interference of waves, I'm going to need to have two of them. So mathematically, we have something here to do with. So that first y sub 1, it's got some amplitude that we'll call ym. We could have used the a for amplitude, but we're going to use the y's here. And that kx minus omega t. So remember that the argument of a sine or cosine function has to be an angle, and that angle kx would be a wave number times some distance, giving us some angular displacement, and omega t is also an angular. It's speed times time, another angular displacement. So the difference is this y2 wave has some sort of phase shift to it. So it's not the same wave. All right? It's offset. So these two waves will interfere with one another if we give them a place to do that. All right? So this is our starting point. So we're going to add them. It's the idea, waves running into each other. We're going to add them. So y1 plus y2. Well, they have a y, their amplitude is in common. All right? So we'll do that, and then they're going to have these two angles with their different phases. So here we have these two different things. If it were only the case that these two things were the same thing, but they are not the same thing. So if we're going to add them, how are we going to add them? Well, the other day, don't remember, I thought I showed you, but in case I didn't, it is the case, and you may not remember this, but you would have been exposed to it at least once in your trig class. To that identity, which I know just is the most thrilling thing you've seen all day. You can't wait to play with it. It's harder than it's easier than it looks. All right. So we could work all of this out and plug in Chugsville and all that jazz. But let's go ahead and think this through here. So if I'm going to do so there's two parts to pay attention to here. There's what is the a plus b part and what is the a minus b part. All right? So that's where we're going to have all of our fun here. And so let's just tackle that one piece at a time. So what would alpha plus beta be if we just take those pieces out, because literally all we have to do is half of that is the sine argument. And that may not be obvious when you look at it, but let me write it. Really what it comes down to it, this thing here is going to be the argument of each sine and cosine. That's implied when you write sine. You don't have to necessarily put parentheses and everything in it. It's implied. It's assumed that that's the case. So whatever follows sine, cos, whatever, is the argument of that function. But we don't always write it that way. Okay? But I just did. So, yay. So alpha plus beta. Well, that's going to be 2 kx minus 2 omega t plus theta. And so that's just adding them. I have 2 kx's, I have 2 omega t's, and this phi, the phase shift. Just adding them, all right? And so half of that is just going to be kx minus omega t plus half of phi. All right? And alpha minus beta, well, I have a kx minus a kx. That's no kx. I have a minus omega t minus a minus omega t, which is no omega t. Okay? And that just leaves me with 1/2 phi. So we go and plug all that stuff back in. All right? And I'm going to go to a new screen to do that. That means our y1 plus y2, we're going to have 2 of these ym things, and then applying the rule, and I'm going to put the cosine part first. The alpha minus beta part was just a 1/2 of that phase shift, and then the sine thing was kx minus omega t plus the shift. All right? And so this really is y as a function of x and time. All right? Now, why did I take you through all of that? Okay? Because the math is we're going to get 2 things out of the mathematical analysis today. So, and the math is one way to see what's going on here. So if that phase shift is 0, okay, then your amplitude is just 2 times that y height, whatever that y height is, okay? And what that would mean is that these things are completely in phase. Which means they would be fully constructive, okay, because a maximum from the wave y1 coincides with a max from y2, and you get a bigger wave. And bigger wave meaning that double. So remember, both of those y functions, we just had an amplitude of 1, whatever ym was. Okay? And now that I've added them, I have double that. And so with no phase shift, that phase angle, if it's 0, then they are identical waves that when they add together, produce twice as big a wave. And so at max amplitude, each wave contributes and they double when they add together. So that means a wave that's, oscillating this way will now double its amplitude. That would be the maximum behavior. So that's one way that we can look at it. If that phase shift is equal to pi, then the amplitude is 0. So why did I pick pi? Okay. Well, what's the cosine of half pi, of pi over 2? 90 degrees, it's 0, right? So we do this all the time in science. 0 points are one of our favorite critical points, because if I pick an input that produces a 0, that gets me as close to a simple, it's a critical point, these zeros, when they work out that way. And so I get no amplitude at that. And so what that means is that they are completely out of phase when they add. Fully destructive. And so what you have here, max from Y1 coincides with max from Y2, they cancel out. Amplitude 0, wave gone. So anybody have noise canceling headphones? Basically, that's what's going on. It's what's the incoming wave form. So I generate a destructive pattern that is out of phase and equal magnitude, and it will kill that noise. That's essentially what happens with that piece of technology. White noise generators would be just destructively kind of, they don't cancel it out, otherwise you wouldn't hear anything, but they just sort of they just literally wash out other frequencies in varying degrees. But what they don't do, like huge wavelength frequencies, so like when I put my white noise machine on at night, I still hear my idiot neighbor when they pull up in their hell yeah thumping stereo. I hear the thump thump because it's just too much. Okay. Other noises I don't hear. Other stuff out in the house that are frequencies closer to that white noise generator. So I need a hell yeah white noise bass thing or something, to a bass white noise or something like that. But not that I'm one to complain about my rude neighbors, all right? So waves, they behave this way. And so one practical thing of paying attention to all this mathematics is, one, the mathematics does tell me that, and then there's some profitable electronics that go along with it that some folks have, like Bose. They're pretty good at this sort of thing, but I think you need like $300 to get their noise canceling headsets, all right? So that's that. All right, so that's interference of waves, and we started our adventure with the standing waves, and I think I just got my note pages out of order, but let's take a look at standing waves. Here for a minute. All right, so let's use those same models there, except this time the only thing that's different about these two waves is going to be their phase angle. Everything identical except what's happening inside of the angle. So they're the same speed, frequency, okay? So let's do this. Assume same speed, frequency, and amplitude. But what you have here are plus and minus x directions. Okay? So these are not going the same direction, they're going at each other. And so if we want to have, the full wave, we're going to add them. That'll just be the sum of those two things, so we'll just write it as simply as it can be for the moment. That's what we need to do for this standing wave. If they're going to be standing waves, so there's what you add waves, and either they stand or they interfere. And in the interference, they either something between fully constructive, adding of maximums, to fully destructive, canceling out of maximums. Whole range of possibilities there. So we did that one. Now standing waves, you add waves. How do they shake out in this game? And so adding y1 and y2 would have that similar thing that we saw a little bit ago. You're going to have sine kx minus omega t plus sine kx plus omega t, because of the way we set this up in our case. So again, we would have to go through all of those motions with that trig identity. I'm going to spare you that, all right? And what you get after going through all of that rigmarole which isn't entirely necessary. Is this right here. So if we were to apply all of that alpha, beta, add it, subtract it, half, etc., we would get that shake out of our tree. So let's pay attention to this piece of the puzzle here. So this entire equation here it's missing something that would make it a traveling wave. It is not of the form that we started with, okay, where you have some sort of function of kx plus or minus omega t. It's not traveling, okay? Not a traveling wave. So that's what you saw in that one video demo. Those are standing waves. The pulse wasn't moving. Well, the pulse wasn't moving along the x-axis. The pulses were moving between amplitudes. So a standing wave is not a moving way in the plus or minus x direction. So the mathematics explicitly tells us that it's not a moving wave. Granted, most people would not think to ask that question, right? It wasn't like that was the first thing that popped into your head. And I don't expect that the other physics class, full of wannabe engineers, will see that right off the bat. Almost nobody thinks that way. Okay? And the expectation at this stage of the game in physics, introductory physics, is you would go, oh yeah, I see it now that you've said it. But nobody essentially immediately goes, oh, it's not of the traveling wave type, therefore it must be standing. But because it has no varying phase angle, okay, there's no offset to it at all, it's a standing wave. All right? So that little, if it's not a standing wave, or it's not a traveling wave, then it's a standing wave. So I saw it with my own eyes as a standing wave, and then there's the math that demonstrates necessarily that it's a standing wave. Okay? And that's subtle, to say the least. So if your sine of kx equals 0, which is what we're dealing with. So just to give it back on screen here, our y1 plus y2, the adding of those waves, gave us this form here. So we're paying attention to that now. If that is 0, then there's no displacement of the wave. Therefore, anywhere where you have x, your x value is some number of these, okay? These are nodes. So this is a slightly more, well, this is the complicated version of what we saw in the first part, okay? We could see the nodes in that one video. We did some basic math to show that those nodes separate half wavelengths. There's always an antinode between any two nodes, and every antinode is a half wavelength. It's associated with the half wavelength and counting them. All right? And K, in this case, K is the wave number. It's not the spring constant, even if you're wiggling a spring, okay? It's a wave number, all right? And so we have that. Those are what we call nodes. Now, a question. Where is displacement a maximum? And the answer to that what does sine vary between? What is the maximum value you can get for the sine of any angle? in fact, sine and cosine both oscillate between the same two numbers, just at different opposites. What's the radius of the unit circle? 1. So sine maximums will be at a plus or minus 1. Now what I don't expect to be obvious, but I'm going to write it anyways, is the x value that's the structure, okay, of antinodes. And if you remember, let's just do the fundamental one, since it's the easiest picture. So here's a standing wave. The nodes are the parts that are fixed and not moving, and the antinodes are always between, because they're moving. That's where amplitude is happening. All right? And so at a maximum, you would be oscillating between that max plus and minus 1, the sine of whatever that angle is. All right? So that's the end of the wave abuse in terms of just the theoretics of it. And so my main goal, I think that it would be great if the last two things we did, the mathematics of the standing wave and interference wave, were as straightforward as just the fact that the length of a string will always work out to be some number of half wavelengths. Or you could say some number of half wavelengths will be the full length of your string when it's vibrating in this manner, producing standing waves. You can see that with your eyeballs, and the math we did was really low-level algebra. And there was a law that we could build from that. The rest of this, well, it's one reason why we made you take pre-calculus or trig, is so that you could look at this without, having a brain aneurysm or something like that. All right. Spared you some of the mathematics, but hopefully you can see that, when I look at something, how do I understand what that equation is? Life science majors don't have to bother with as many as engineering and the hard science majors do, but you still have to. And so Nectaria will have the hardest hill to climb because she has to be a biochemist. So, but the rest of you have varying degrees of, do I just use the equation? Do I understand it? And so one of the goals of your education is that you would understand it as opposed to merely using it. Have a couple pharmacists. Who's going to do pharmacy? We want the pharmacist to not just recount all of the facts, but to actually understand how they work together. Mathematics is one of many tools that lets you do that. I don't think, at least I hope, that nobody at the pharmacy has to do this math. Nobody does this in their head fast. Okay? You're doing ratios and stuff like that, but those ratios are connected with biological and chemical facts. All right? And so quickly being able to understand those and what the impact is, that's a big deal. All right. So all of that to say, look for critical points. That probably is the most practical and useful for the life of a scientist. If you know where the critical points are, then you're golden. So here's this. This is super basic problem type. I have a few that are like this in this set, and then a couple that are not as basic. All right. So wave's got this speed, it's got a wavelength. What's frequency and period of the wave? So this is a kind of problem that is set up nicely to use that equation that I was saying was so super duper basic. All right? And so we have wavelength and speed data given straight up out of the problem, and so this 240 meters per second over 3.2 meters means we have this 75 inverse seconds, if you will, because a meter per second divided by a meter is a per second, whatever that is, all right? And so what we call that means that the frequency is 75 hertz. That's the big idea, if you will, is what do we mean by inverse seconds? Okay, it's cycles per second. That's what that is giving us. And so that gives us part A. And then part B, if we want to know the period of the wave, we know that frequency is 1 over the period. And so we're just going to get 1 over 75 hertz. And that works out to be a really exciting number. All right. 1.3 times 10 to the minus 2 seconds, which would be 13 milliseconds. 13 1,000ths of a second. Okay, that's what the milli thinks. So nice, easy problem, plays well with the other children, doesn't give anybody much grief. This next one, move up in the food chain just to ever so slightly do that. And so again, our equation, this time we're going to need wavelength is the thing that we can get right off the bat because we have its speed and its frequency. That amplitude piece of information, we'll get to that in a minute. Okay, but right off the bat, I can leverage the fact that it has this frequency and that speed. And so 330 over 550, everything's in the right units, so I don't have to really worry about that right now. And I know that I'm going to get a wavelength, and since it's a length, the right units are going to be meters in that case. So we're going to get 0.6 meters. 00 meters if we wanted to pay attention to significant digits. That doesn't really matter. Okay. Then there's this thing called the angular wave number, and we used it a few minutes ago. All right, and it happens to be the case that K, which is previously used for the spring constant, but that's not what we're dealing with, is 2 pi over lambda. So just think about that number first before we move on. The reason why we're going to need the wave number is because our next thing to do is write that equation. And if you remember, one of the things in that equation in the argument for the angle was that kx thing and then an omega t. All right? So a wave number, let's think about it. 2 pi, that's one complete trip around the unit circle. And how many wavelengths per complete cycle? That's the wave number. Okay, so it's a relatively simple ratio if you think about what the symbols are referring to. And that's one of the reasons why people don't do well in math and then don't go into science, is that the symbol-referent connection is not something that we're generally concerned with in a math class. We're concerned with you obeying the rules of math. And when it just refers to itself, that doesn't make a lot of sense. But anyways, I'm not going to rant too much about math. problems. All right, so 2 pi over that, and so 2 pi over the 0.6, and we're going to get 10.5 inverse meters, because it was over 0.6 meters. All right, so that's a weird number. But if you think about it, k gets multiplied to an x, so I get something over meters times meter. That means I get a number, and that's what those sine, cosine functions need. They need just a pure number, or radians, to dump in it. So on one level, we get this strange unit, whatever an inverse meter is. It makes no sense. Didn't make any more sense than an inverse second does. Okay? It's a something per meter. All right? How many complete trips per meter? If you think back to the wave number. All right? So we have that little piece of information. It's also true that omega, we've seen this before, is 2 pi times frequency. And that means that our 2 pi times the 550 hertz that we already know about is going to give us 3.46 times 10 to the third inverse seconds, or hertz if you will. And that means that now I believe we have everything we need to write our equation, which needs to come in the form of some amplitude times the sine of kx minus omega t. And that means, all right, amplitude, right here, an amplitude of 0.1 meters. So 0.1 meters will be my amplitude, A. And then we're going to have the sine of what? Well, that K was a 10.5 inverse meters, 10.5 inverse meters times X, all right? And then we're going to minus omega. Oh, I sort of ran out of room there, so I'll have to crunch it down on the... Yeah.
Amplitude isn't supposed to be 0.01.
Oh, yes, thank you. I'll have to fix that here. So we have our function here, but I got to fix that piece of the puzzle. 0.01 instead of 0.1. So that's our function. Yay! We wrote the function. So what practical use would anyone have of this sort of thing? Well, going back to the noise canceling bit, this isn't a noise canceling problem, but this would be the kind of, somebody would have to put this code onto a chip in that noise canceling headset. So just like we put the physics into multiple Visual Python things where we got all this world stuff and then 3 lines of physics, same thing. All right? So in a sense, that sort of noise canceling headphone device, it's got a simulation going. It's got a sensor that senses various frequencies and wavelengths, blah, blah, blah. And then it builds a function to match them with a minus sign, basically, and cancel them out, like we saw in the other things. And so this sort of math has to be under the hood of these devices that we love to spend money on, et cetera, all right? You know, I wonder, just it comes to mind, remember we talked about the toothbrush, the ultrasonic toothbrush? What if somebody comes up with a way to, like, give you a pill that, you know, if you got an infection, a bacterial infection, and just instead of you taking antibiotics, it shakes the hell out of the bacteria as it goes through your body, but it doesn't shake the hell out of anything else. So what if it were the case that the bacteria get shook to pieces by this thing, but nothing else does? It's probably not likely, but who knows what we'll come up with. You know, we're already working on ways where things can go to your body, and they go to places where this is true, and they do stuff there only. You know, like killing cancer. So that's the next wave. You know, if we're lucky, if I'm lucky, they'll get that all worked out before I'm too old, and then I can take that pill. It's almost certain that you will have that before I'm old. I'm 52. That's not old yet. I got a long ways to go. Like 30 or 40 years before I'm old. All right. At least that's what I'm going to tell myself for the indefinite future, until I forget. They say the first thing to go is your memory. I forget what comes after that, but the fifth thing is your memory. So, all right. This one, the speed of a transverse wave on a string. We're on this theme here. What you don't know, but I'm going to tell you, is that there's this nifty version of speed for wavy things, and we wouldn't be able to do this problem unless we knew that the speed could be a function of force and mass density of this matter wave. So there's all sorts of waves. There's matter waves, which is strings, like the guitar strings, and et cetera, et cetera. There's sound waves, okay, stuff you hear. There's light. Light can behave as a wave. Electromagnetic radiation is understood as a wave. So and in fact, for those continuing on, when we talk about the optical tweezing of the DNA molecule, instead of other boring things in electricity and magnetism that the engineers have to endure, electricity, electric fields, fluid forces, lasers. These are features of the toy that let us stretch a DNA molecule like it were a spring, and understand things about DNA that we wouldn't have known before we had the toy. It's been around for your lifetime, maybe a little longer. All right. So here's this equation that we can use, and that's great. The speed of a transverse wave, okay, yay, we have that speed. The string tension, or this force, 120 newtons. So what value must the tension be changed to raise the wave speed to 180 meters per second? All right. Well, we need to unsquare root this business. So this means v squared would be f over mu, which means we could get to this sort of function here. And so along the way, we have to figure out what this mass density is of this wave. So 120 newtons over 170 meters per second squared. And we're going to get a mass density 4.15 times 10 to the minus third kilograms per meter. That's a linear mass density for this waveform. And so now, to what value must the tension be changed to raise the wave speed to 180 meters per second? Well, I can just take that same function, okay, namely this one, or any one of these, and I could just say, you know what, the force, the new tension, to get that speed, so this is going to be the force value or new tension, because the string didn't change. So now I've identified this property of the string that was material to this force speed function, mu v squared, and so mu will be what it was before, And the speed that we were looking for was 180, and that's getting squared. And so the new tension works out to 135. So it's an increased tension. Increased speed ought to be increased tension. Of course, the function sort of demands it. So that's easy, but you would, of course, have to know that this equation even exists. And now you do. All right. So sometimes we can derive every equation, and if we had to derive every equation in a course like this, then we would need a whole year just for this, which wouldn't bother me any, but I suspect other people wouldn't be as excited. All right, let's continue along that pattern here, but this one gets a little more complicated because we're going to look at a few different things. And there's average power involved here, so we'll have a new equation associated with that I'm going to give away. But just this is more of a how well connected all the dynamics are. Okay, that's really what this is a demo of. So a string, it's that long, it has a mass of 260 grams, there's a tension on it. What must the frequency of the traveling waves of amplitude of so much for the average power to be 85 watts? So getting this to obey our power limitations. So though this problem isn't, I'm going to keep going back to the noise canceling headphones that somebody brought up. Guess what? In the design of that toy, somebody had to figure out, okay, the battery life is this much, that where the power expenditure needs to be this much. Can we do it? Either we can or we can't. If we can't, we re-engineer materials and da-da-da-da-da until we get it to work. All right. So tension, all this stuff. Well, it is the case that the linear mass density has to be the total mass over the length. Technically, you didn't need to come to college to figure that out. You can have all sorts of densities: volume density, area density, linear density. Okay, so the mass density would be the mass of the thing over its length. And so we were told that it was 260 grams. Well, that is 260 times 10 to the minus 3 kilograms. Remember, we got to use kilograms instead of grams. The length was already in meters, so that's good. And so now I have mu, the mass density that we saw in that other equation, because I'm dealing with forces and whatnot, so I'm going to need to know the mass density of the wave, or of the string. And that means I can go right back to this equation that we saw before, but didn't get to use in this exact form. So we have 36 newtons right out of the problem. Mass density that we just solved for. And we get 19.3 meters per second. That's moving pretty fast. Okay. So 3 meter long string, 3 of these yardsticks. Kind of like what we saw in that video. They had a 2 to 3 meters spring they were wiggling in that demonstration video. And so we could have done a similar thing if we had that spring, its mass density or its length, whatever. All right? And so we have that. Now, what you don't know is there is this equation that relates angular speed to average power. That's what the P with a bar over it is. And it has mass density going in it. It has the speed that we just computed and the amplitude, square of that amplitude that we saw. So, yeah, we didn't derive that, but we need to know it. And so that means omega will just end up being the square root of all of that, okay? And we can plug and chug all of that. All right, we're going to get a number, and the number is going to be 1.24 times 10 to the third radians per second. Okay, so think of it. That's 1,240 radians per second. Okay, so divide that by 2 pi, to get how many revolutions per second or minute that might be. That's cooking, right? As an angular speed. But the strange thing here is we're not talking about something that's going round and round, but the mathematics is. The mathematics of sinusoidal functions can be understood that way, even if it's not dealing with rotational motion. The math is the same, all right? And so at the end here, that means the frequency is just going to be omega over 2 pi. So you think about it, the speed per full revolution. That would be the frequency. Speed, angular speed per full revolution is how frequent the wave is therein. And so that works out to be 198 hertz. Again, I'm not concerned in this class with every little plug and chug piece of the puzzle, because it's algebra, and you can do that. What's useful here is just knowing that we can, with a little bit of information, we can get a lot more. Every science has that going for it. Every science. Period. And it's how you use that information and just knowing that you can use it for these other things. And so every physics course, that's a fundamental goal. Some physics courses, learning to do more math is also the goal. All right. For this one, this problem, it's really just a demonstration. And some of the things are straightforward and obvious, other things are not. And that's just the way that goes. I'm going to skip this one because we've sort of already done that sort of thing. All right. And keep it a bit simpler. So, a nylon guitar string. So I was playing a steel guitar string a little bit ago. Nylon guitar strings are under a little bit less tension. I could have brought my classical, but I think it needed new strings, so I didn't want to mess with it. And so, and under a tension of 150 newtons, so remember a newton is about roughly a quarter pound. So if you divide this number by 4, you have about how many pounds force these strings would be under. 90 centimeters apart, that's almost a meter. And if you think about it, look at the length of my guitar. It's less than a meter, but heading there. And so this is a realistic problem. I guess there's no figure here. I forgot to add it in. So let's do our business here. So this will be this, just like we saw initially, we have this standing wave, so it's all right, go in there. And so every time I play a chord on a guitar, I'm changing where the wave is fixed. I'm putting, basically, if I'm playing well, good sounding but unnatural nodes, because I'm pinning the waveform down and making the string vibrate everywhere else, making its amplitude, forcing its amplitude to be somewhere else other than that node where I put my finger to hold that string down and make the wave wiggle around that node. Okay, so music is manipulating that whole node anti-node thing away from the, I guess, the natural state of those vibrating strings, just open, nothing holding down except at the very ends. All right, so those relative changes are what make music appealing or not if somebody's doing a bad job. All right, so part A, calculate the speed. All right, well, we've seen that before. We have a speed equation that deals with the force that I know and the mass density that I've been given. So this is easy peasy. Square root of 150 over the 7.2 needs to be times 10 to the minus 3 because grams per meter. It needs to be kilograms per meter. So this is newtons, kilograms per meter. And we get a speed of 140 meters per second. Just think about it. So those chords I was playing and the harmonics, we're talking about speeds of the wave, the moving part of the wave, 100 plus meters per second. Just on that string there. Again, these big things smashed into small spaces. All right? Have a noticeable effect. So let's go back to that. I want to keep trying to tie it into things that we seem to understand already. So we know that at thousands, like tens of thousands of hertz, you can shake a bacteria to death, like the toothbrush thing. Probably make the string break. We got it up to those speeds. Okay, but you know the relative differences in outcome and the space involved. So the space that this guitar string would vibrate over is massive compared to the space over which that ultrasonic frequency from a toothbrush is going to wipe out bacteria. Get down to the size of bacteria, okay, and that's part of that puzzle. They are this size. So there's a range of frequencies that are for them. It must be the case because ultrasonic toothbrushes don't mess up your gums. Well, brushing too hard with anything, that messes up your gums, but the frequency apparently doesn't mess up your tissues. Because I've used those sonic toothbrushes before, and you know my teeth didn't fall out of my head. All right, and millions of people buy those things, and they do just fine. Dentists recommend them. You know, they've been on scientific studies, so unless everybody's in a big conspiracy, along with, I don't know, the flat earthers and moon landings fake and Jupiter's on spaceship and all sorts of interesting things that are out there in the web, these things work. So I wouldn't be surprised if one of the novelties that comes out, if it hasn't already in medicine and life sciences, is using sound frequencies to kill bad things in you. Just, it's how do you deliver it? You know, it's easy to put a toothbrush in your mouth. It's hard to deliver that same thing at the cellular level on the inside of your tissues. Somebody will figure that out, though, I suspect. And what that means is since I said it and don't know, that means somebody already has. I would be... Somebody go look it up. All right, part B. Find the wavelength. Okay. Wavelength. We just did this a little bit ago. Remember, this right here, that's the wavelength. All right, and so it's going to be 2/3 of the length. The way this is set up, given that I know the nodes. And so this is easy. 2/3 of the 0.9 meters, and I get 60.6 meters or 60 centimeters more natural, I guess, version of the number. And then part C, they want to know the frequency. So frequency, this is just taking that ultra basic, velocity is lambda frequency, rearranging it, 140 meters per second over the wavelength of 0.6 meters, 240 hertz. So just like for instance that A string, when I was plucking A has a frequency of 440 hertz. A440. We tune a lot of things to A440. All right? And so other strings have higher or lower frequencies. Okay, so, but they're always in the hundreds, at least for the open. Now, really high-pitched things up higher, like the harmonic, will be at a higher frequency, maybe double or something like that. So some of those frequencies will get to the thousands, but just the natural ones for strings are going to be in the hundreds. And so this problem is basically modeling the way that it really is on a nylon string guitar, a classical guitar. So one of those strings has that going for it, and I don't remember if I ever, I'm sure I used to know. I just don't remember what that is. All right, another string. Actually, I'm going to skip that one too. And we don't need to do that one, and we're done.